Good afternoon. So we're going to discuss optical instrumentation in this chapter. So far we have mainly discussed paraxial optics. That is, we have focused on rays that are close to the optical axis. That is, for example, if I have a lens here and this is the optical axis, right? We stayed close to the rays that are close to the axis, right? So we were within this range. We were not considering, for example, rays um, that are marginal, that are up here. Um, so we were not considering the rays that were, for example, that were here. So we were not considering these marginal rays. But in general, these marginal rays are also there. So you use things like apertures and slits to avoid, for example, marginal rays. So you could say you could put an aperture here to get rid of a marginal ray. So the paraxial approximation is pretty much valid in that sense. But nevertheless, there are other effects. Even if you just allow these rays, there are other effects, other aberrations that appear that we will study in this chapter, and we will also put to use the matrix methods that we have learned to describe or understand some of the optical instruments. And we also need to learn a little more about the kind of optical defects that exist, because parts of optical instrumentation are essentially dedicated towards the design of correcting these aberrations. One of which we will see today, the achromatic doublet that is used to correct for refractive index dependence on the wavelength of light. Okay, so to do this, first let's quickly recall what we had done in the matrix method. So we designed a system matrix which in general could be labeled as BC minus A minus D, right? These elements B, A, B, C, D, you can determine them by looking at the lens. For example, if you have, say, a thick lens, right? If you have a thick lens of thickness, say T, right? If you're given this lens, then you know that you have a light ray coming to point P1 here, right? Undergoes refraction here, right? So it undergoes a refraction at that place. Then it undergoes a translation, right? And then it undergoes another refraction at point P2. So that is the second refraction, right? You know the matrices for refraction, translation, and the second refraction. Right? So you just basically put in those matrices, which are essentially dependent on the geometrical factors of the lens, and from there you essentially can get the system matrix, right? So it is the system matrix. The elements A, B, C, D are essentially dependent on the geometry of the lens. I just would like to remind you that these A, B, C, D, the elements of the lens, are not some elusive numbers. They're just rehashing the geometry of the lens. Okay, it's just to make our life easier, to make analysis easier. So now let's see how to build a simple telescope, for example, right? Especially let's look at the design of the Keplerian telescope, right? So we're going to look at um, Keplerian telescope, right? So in Keplerian telescope, the idea is to look at uh, uh, very distant objects, right? So you're trying to collect light from very distant objects, and you would like to have you would like to view a big image, a large image of that object. So you would like to have an objective collect the light, make an image, and then have an eyepiece that can magnify that image such that you can view not the image that is formed by your objective directly, but by a magnified image that is formed by your eyepiece. So you'll have two lenses. So first you have a large objective. So this is the objective, right? And let's say the objective has, let's say, a focal length of f0 or fo. So let's say it has an optical axis like this. So let's say it has a focal length of f0, right? And so that is where the image will form. And let's say from here, let's put another eyepiece here with a focal length of fe, right? So let's have a smaller eyepiece here. Right. So now when ray of light is coming in here, right? They basically form an image essentially here. Right? They form an inverted image right there. Right, and the rays of light that are going into this eyepiece, they're going into this eyepiece that is here. The rays of light that are going into the eyepiece get refracted. So they get refracted, and when we are viewing at it, so if you're viewing, this is your eye, right? And when we are looking at it, it would appear as if these rays of light are coming from a distant object that is here, right? So this is the final image that you see, right? So you know the focal length f0, you know the focal length of the eyepiece fe, right? This would be the height of the image here from the objective. This would be the height of the final image, right? Final image. So then now if you want to analyze this, you can just simply use your matrix method, because this you know the matrices for this one, right? And recall that we have actually developed what I call as a door-to-door matrix. That is, if I go one slide back, we actually took a thick lens. We went from a point here, where that was at a distance d1. We went from here all the way to a point that was at d2, and we developed a matrix that goes from this point all the way to another point that is at the other side. I hope you are able to recall what we had done there. And when we did that, we saw that we got a matrix, and we had to we got something like if you recall, we got something like b plus ad1 minus 1 over the focal length 0 and c minus ad2. We got something like that, and we saw that this was 1 over the magnification, and this was magnification, and we set this basically to magnification, 1 over magnification minus 1 over f0. This was the matrix to go from door to door. That is, if I have a lens of focal length f, and if I have a ray of light coming from a distance d1, and it is going somewhere to d2, right? And this lens is defined by b minus a minus dc, right? Then to go from point d1 to point d2 through this lens, you basically essentially this is the matrix, right? That is the door-to-door matrix is what we called it. Right, so we developed this matrix already, and if you don't remember it, I suggest that you go back and look through the lectures there. And if you do remember it, I'm sorry for boring you again. But essentially that is what we are doing here. Here the object is coming from the object is at infinity, right? And then but the image is essentially forming here, but all that information is included in the magnification, right? So essentially, what we could write is the first matrix that is forming here is for the first objective would be uh, 1 over the magnification 1 of the lens 1, right? And this would be minus 1 over the focal length of objective. Then you have 0 and magnification of 1. That is for the objective lens, right? And this includes door to door, so the rays coming from the distant object and forming the image. And then for the second lens, again the same thing. So for the second lens, it would simply be 1 over m2, right, minus 1 over fe 0 m2, right? So why I'm writing this is you don't have to do the ray diagram. If you know your lenses, that is essentially the geometric parameters of the lenses, you know your lens matrix. If you know your lens matrix, these M, Fe, F0, you know these as the matrix elements. For example, this M1 is C plus AD2 or C minus AD2, right? So these A, B, C, D are matrix elements which you know from the lens, and D2 is the distance to the object, so distance to the image. So this is the thing that you know experimentally. So you know this value. So you know the magnification. So even if you're looking at, say, a very distant star, you don't know the real size of the star. You have no information about it, right? You cannot really go to the star and measure its size and compare it to the image size to know the magnification. Nevertheless, just through simple analysis, right, you can know what the actual size of the star is because you are able to gather it from the other information that you have, right? You have to appreciate the beauty of this, right? So I hope you are able to you're able to see what I'm saying here, right? And that becomes much easier once you have the matrix method. It becomes much easier to see that just from C minus 82, I would know the magnification, right? And from the magnification, I can get essentially the actual size of the object, right? Okay, um, that's that's the Keplerian telescope and how we can use matrix method there. So now let's switch gears and let's discuss the refractive index and polychromatic light. So the refractive index we have been discussing as if this refractive index is a constant, but in reality this refractive index is not a constant. It is indeed a function of wavelength, right? And this is sort of well known because if you look at a prism, prism disperses light because each color refracts at a different angle, because the refractive index for blue is different from the refractive index for red, right? So in general, you can express an empirical relationship based on, this is purely based on observation. So Cauchy, Augustine Cauchy, I don't know what's happening. Augustine Cauchy, he basically from empirical relationships, he established a relationship, some constant, by fitting a polynomial curve, something that looks like b by lambda squared, c by lambda 4, so on and so forth, right? And and so you can use this relationship to sort of develop one dispersion that is dn by d lambda, and it's roughly something like minus 2b by lambda cubed, where this a, b, c constants are essentially empirical, right? And they would depend upon the material. For example, A, B, C constants for glass would be different from quartz, because the refractive index itself is specific to the material, and how that refractive index would change based on the wavelength is also particular to that material, right? So you have to experiment with that material to know how refractive index for that material is dependent on lambda. Why refractive index is dependent on lambda is what we will study later in the course. But for now, it suffices to say that refractive index is dependent on lambda, and this is an empirical relationship. Although people did not understand why it was dependent, they were still able to develop an empirical understanding and an empirical relationship. And this is an issue in developing optical instrumentation, because if the refractive index is different, as you can imagine, if I have a lens, right, and say I have white light from the object, right, and let's say now I have blue light going from here, right? Now you see that it is inversely proportional to lambda here, right? So blue light has lower wavelength. Blue light is say 400 nanometers, right? Lower wavelength, so higher refractive index. So if it is a higher refractive index, basically it would focus somewhere, say here, right? Now from the same object, if it's a white light source, then from the same point, if I have red light, for red light the wavelength is 900 nanometers, let's say, or 700 nanometers, let's say, right? 700 nanometers, then the refractive index is lower than that of blue, right? And because the refractive index is lower, right, then it's going to go here. Again, if you don't know how to analyze which is going to go farther or nearer, think about it this way. If you have a lens, right, let's say if you have a lens and you have, let's say, a ray of red light and a beam of blue light going simultaneously, then blue light has higher refractive index. That means it goes slower in glass, right? And because it goes slower, it's not going to go farther, so it's just going to end up here, right? It's just going to end up here. And red light is going to go faster because it has lower refractive index, so it's going to go faster. That's why blue is here and red is there. So what you're basically is going to see is this blurred image through the lens, because blue and red have different refractive indices. So this is what we call as a polychromatic aberration. Right. So the way we can look at this polychromatic aberration is we know that 1 over, for example, for a lens, 1 over focal length we know is the refractive index minus 1 over R1 minus 1 over R2. This is the thin lens we developed, thin lens equation we developed earlier, right? When we were studying pure geometrical optics before we started the matrix methods, right? So essentially, the refractive index is what is different for blue and red. So if I change this n by a value of delta n, if n goes to say n plus delta n, if the change in n is delta n, then f will change by delta f. So I can just differentiate this equation. So if I differentiate this equation, I would have minus delta f by f squared is equal to delta n 1 over r1 minus 1 over r2. Right? But from this equation, I can write 1 over r1 minus 1 over r2. But I can write 1 over r1 minus 1 over r2 as 1 over f times n minus 1. Right? So that's what I'm going to do. I'm going to write 1 over r1 minus 1 over r2 as delta n 1 over f n minus 1. Right? Then I can cancel one of the f's, and I can write minus delta f, right, is equal to or plus delta f is equal to minus f delta n by n minus 1. Right? I can write delta f as minus f delta n minus 1. So this represents the chromatic aberration of a lens. I'll write it on the next slide again. So the chromatic aberration of a lens, the chromatic aberration is delta f is equal to minus f delta n by n minus 1. Right? Okay, so if you want to calculate the chromatic aberration for say between blue and red, the delta f